Okay, now we have another example. The example number 3 is about a dragster car that has a mass of 1.3 megagram, which is something like 1,300 kilograms, and the center of the mass at the point G. Well, actually, this drawing is not very clear, but you can see the figure below that the point G is going to be here, and this is the center of the gravity that we're going to deal with. Okay, so that's the point G that we have. Okay, so the weight is going to go downward at that point. Now let's continue with the thing. So we have a parachute is attached at the point C at the end of the car with the height of 0.75 meter above the point G. And that parachute is going to provide a horizontal braking force of the F is equal to 1.8 V square Newton, where the V is going to be in meter per second. Now we need to determine what will be the deceleration that the dragster can have upon the release of the parachute, such that the wheels at the B are going to be on the verge of leaving the ground. So that's me, we are not going to have any normal reaction at the B point. So this one is going to be hardly touching the ground, so no force is going to be there. So what we have in this scenario is that the point G is going to have the weight, the point A is going to have the reaction from the ground is going to be the NA, and the force F is going to be dragging the car backwards, so it's going to stop it. We need to know what will be the amount of the deceleration we're going to have in that case. We're going to neglect the mass of the wheels and assume that the engine is going to be disengaged so that the wheels are going to be free to roll. So this actually what we have is to the left is the free body diagram and to the right is the kinetic diagram. So once again, the solution list has been submitted to you or something like that. You can see that we need to sketch a free body diagram is going to be drawn first. We're going to have the same equations like the sigma forces to the x-axis is going to be equal to the mass multiplied by the acceleration to the x direction, and the moment around the point G is going to be equal to 0, and the sigma only forces to the y direction is going to be equal to the mass multiplied by the acceleration to the y. And by solving, we should get that the reaction force at the point A is going to be equal to 12.7 kilonewton. The velocity of the car is 109 meter per second, and the acceleration should be 16.4 meter per second square. And that's how we are going to show you how we got these answers. So we start first with defining that we have dragster translation, which is going to be rectilinear. And the diagrams is that this one is going to be the free body diagram, that the point G above the point G by 0.75 meters, we're going to have the horizontal force F, and 1.25 meters away from the point G, we're going to have the vertical force NA. The NB is 0, but it's located at 0.25, at 2.5 meters from the point G to the right. So in the kinetic diagram, we can see that the center, we're going to have the mass multiplied by the AG is going to drag the force to the back. We need to find the value of the AG. So we're done. We are going to have some analysis, like the force, for example, is 1.8 V square, because going to the left is going to be negative. So that's what we're going to define here. The mass is 1,300 kilograms, is going downward. The MB is equal to 0 because the wheels are going to be on the verge of leaving the ground. So the unknowns are going to be the acceleration to the x is unknown, to the y is 0. We're going to assume all, and also we don't know what direction A. And we need to assume that all is going to be positive in calculation. Now set the equations. So once again, the forces to the x-axis, the force to the y-axis, and the moment should be equal to what we have on the kinetic diagram. In the kinetic diagram, we have that the moment should be equal to 0. So this will be the key of the solution we're going to start with. Anyway, let's try to find a useful equation from what we have. Okay, so definitely if I'm going to go there, I'm going to the x-axis. Let's go back to the previous page. So if I'm going to go to the x-axis and the free body diagram, we only have that this force is going to be equal to the MAG. In the y direction, here we're going to have 0. But here we're going to have Na positive minus W. And for the moment around G, we're going to have this force is going to have moment to the clockwise direction, the Na multiplied by 1.25. And here we're going to have the 0.75 multiplied by the F force is going to take us to the counterclockwise, and their sum should be equal to 0 on that side. So that's how we're going to do our work. Okay, so we start with the sigma of the force to the x-axis is equal to the MAGX. So the force we have on the free body diagram is negative 1.8 v squared. And this will be equal to the mass of 1,300 multiplied by the AGX. That will be the equation 1. Now we're going to go to the equation 2, which is going to be about the forces to the y direction. So once again, on that side, we have the Na positive minus W negative is equal to 0 here. Okay, so we solve for that, and we're going to get the value for the Na. It's going to be 12.7 kilonewton. That was straightforward. Now the other equation is going to be for the moment. And as I mentioned once again, the moment in the kinetic diagram is equal to 0. On the free body diagram is going to be equal to, I will take that, for example, the counterclockwise to be positive and the clockwise is going to be negative. So the force multiplied by 0.75 minus the Na multiplied by 1.25 should be equal to 0. Now, what we have unknown in this equation is just the V. So we can find that by solving. We're going to get that the V squared is equal to 12,700 multiplied by 1.25 divided by 1.8 times 0.75. So we can find the V by putting that on the square root, and we should get 109 meters per second. Now, simply I can find by substituting the V squared in the equation 1, I can find the AGX, and this should be equal to 16.4 meter per second square to the left, and that's why I give it the negative sign.